knew the world would not be the same. Few people laughed. Few people cried. Most people were silent. Now I am become death, the destroyer of worlds.
And those were the words of J. Robert Oppenheimer, the father of the atomic bomb. After witnessing the weapon he was instrumental in developing being dropped on Japan in 1945. In just a few brief seconds, the nuclear bombs leveled nearly the entirety of two cities, resulting in over 200,000 fatalities and officially ushering in a brand new era of nuclear weaponry. This unprecedented destructive power led Oppenheimer to spend the rest of his life warning the world against and fiercely opposing the development of nuclear weapons globally. So what happens inside the steel casing of a nuclear bomb, and how does it work to release such a massive amount of energy? In 1938, in Germany, chemists Otto Hahn and Fritz Strassmann discovered nuclear fission. This discovery showed that when an atomic nucleus splits, it can release an enormous amount of energy, as described by Einstein's famous equation. As World War II expanded across Europe and Asia, this discovery quickly became a serious concern for the Allied powers. Intelligence reports suggested that Nazi Germany had begun mobilizing its top physicists, led by Werner Heisenberg, a Nobel Prize-winning nuclear physicist, to explore how this new principle could be turned into a weapon. Had Hitler acquired the nuclear bomb first, the tide of the war would have been completely and irreversibly turned. That fear quickly moved beyond the scientific community and became a strategic warning in Washington. In 1939, Albert Einstein signed a letter addressed directly to US President Franklin D. Roosevelt. The message warned that nuclear chain reactions could make it possible to build bombs with unprecedented destructive power, strong enough to destroy an entire harbor and the surrounding area.
Dr. Albert Einstein wrote his now famous letter to President Roosevelt, explaining the urgency of work on uranium fission. Roosevelt, a man of action, moved swiftly. An advisory committee on uranium was appointed.
In response to this warning, the United States government secretly launched the Manhattan Project in 1942. It became the largest and most expensive military science program of its time. The project received a budget of $2.2 billion, equivalent to roughly $40 to $50 billion today, depending on the inflation baseline used. With more than 130,000 personnel involved, the scientific research effort was led by J. Robert Oppenheimer, whom we saw at the beginning of this video. He was an American theoretical physicist and served as the scientific director of Los Alamos Laboratory, where many of the project's top scientists were brought together to design the atomic bomb. The project's objective was clearly defined: to successfully develop nuclear weapons and bring the war to a swift conclusion. However, discovering the enormous energy inside the atom was only a theoretical starting point. The real challenge was engineering and control. So how does an atomic bomb actually work? To answer that question, we need to take a closer look at the internal design of this weapon. An atomic bomb is built around three main parts: the fissile core, the detonation system, and the bomb casing, along with components that help control the reaction. In this video, we will analyze the structure based on two bombs used in World War II, Little Boy and Fat Man. The most important part is the fissile core, usually placed at the center of the bomb. During World War II, the two materials most commonly used were uranium-235 and plutonium-239. This core can be seen as the heart of the bomb, because the entire explosion begins there. Once fission starts, it is the core that releases an enormous amount of energy in an extremely short time. But the core alone is not enough to produce an explosion. It has to be placed under the exact conditions needed for the reaction to begin. That is why the bomb uses a detonation system built around conventional explosives. Their role is to act on the nuclear material at precisely the right moment. Depending on the design, this system can work in two different ways. The first is to drive two pieces of nuclear material together at very high speed. The second is to compress the core from multiple directions at the same time, making the material far denser in an instant. In both cases, the goal is the same: to bring the nuclear core into a state where the chain reaction can begin. The third part is the bomb casing and the supporting components that help control the reaction. These elements make sure the entire system works as intended. The first is the tamper, sometimes also called the reflector. This is the layer of material that surrounds the core. Put simply, it helps keep the core from breaking apart too early when the bomb is triggered, giving the reaction more time to build. At the same time, it reflects some of the neutrons back into the core, making the reaction more efficient. Next is the neutron initiator, placed at the center of the fissile core. Its role is to release the first neutrons that start the fission reaction at exactly the right moment. On the outside is the bomb casing. This outer shell holds the entire device together, protects the internal components, and keeps everything in place until detonation. From this basic structure, American engineers developed two different atomic bomb designs. The first was the gun-type design. In this design, one piece of uranium was fired into another inside the bomb, much like the mechanism of a compact artillery gun. The second was the implosion design. Here, the explosives surrounding the plutonium core were detonated almost simultaneously, compressing the material inward from every direction. Although the triggering mechanisms are different, both designs share the same goal: to bring the nuclear material to a state where a fission reaction can erupt in an instant. The real question is, how does this device actually work to produce such a devastating explosion? When all the components inside the bomb are triggered at the correct moment, the most critical physical process begins: nuclear fission. The process begins when a free neutron strikes the nucleus of a uranium-235 or plutonium-239 atom. When hit by the neutron, the atomic nucleus becomes unstable and immediately splits into two smaller fragments. This process is known as nuclear fission. When a nucleus splits, two things happen almost at the same time. First, a large amount of energy is released. Second, the process produces 2 to 3 new neutrons that fly out in different directions. These newly released neutrons then collide with other uranium or plutonium nuclei nearby. Each collision produces more neutrons and releases even more energy. From a single initial reaction, the process quickly multiplies at an exponential rate. This is known as a nuclear chain reaction. Under normal conditions, a chain reaction is difficult to sustain because many neutrons escape before they can collide with other nuclei. But inside an atomic bomb, the design ensures that this does not happen. When the explosive system compresses the nuclear material, the density of the uranium or plutonium increases dramatically. The distance between the nuclei becomes much smaller. As a result, the neutrons produced during fission are far more likely to collide with other nuclei before escaping. When the amount of material and its density reach a certain threshold, the system enters a state known as critical mass. At this point, each fission reaction produces enough neutrons to sustain and expand the chain reaction. From that moment, the reaction begins to accelerate extremely rapidly. After only a few dozen generations, a significant portion of the core has already undergone fission before the entire mass is blown apart. All of this happens in less than a millionth of a second. The enormous energy released by this reaction instantly turns the material at the center into an extremely hot mass of plasma. A bright sphere of fire, known as a fireball, forms at the center of the explosion. The extremely rapid expansion of this plasma creates a powerful shockwave that spreads in all directions. This shockwave is the main force responsible for destroying buildings and infrastructure nearby. At the same time, the explosion releases intense nuclear radiation, including gamma rays and neutrons. This intense radiation can cause severe damage to living organisms. In addition, a massive amount of heat is released in the form of a thermal pulse. This burst of heat can ignite widespread fires in areas surrounding the center of the explosion. In terms of mechanism, that is how an atomic bomb works. But to fully understand its power, we need to look at how that energy is calculated in theory. In a conventional explosion, energy comes from a chemical reaction. In an atomic bomb, the energy is released directly from the atomic nucleus. This level of energy is far greater. In theory, just a few kilograms of nuclear material can release energy equivalent to thousands of tons of TNT. That is why the destructive power of an atomic bomb is not measured by the actual weight of the material, but in kilotons of TNT. The source of this enormous energy lies in a famous principle of physics: E equals mc squared. Einstein's equation shows that an atomic bomb does not need to convert all its mass into energy. Even a very small fraction of the mass inside the nuclear core is enough to produce an explosion on a scale never seen in weapons of that time. The next critical factor is speed. Fission inside an atomic bomb multiplies through successive generations of neutrons and can increase millions of times in less than a microsecond. This means the entire energy release occurs almost at once, in a time too short for the surrounding material to disperse. Because the energy is released in such an extremely short time, the temperature at the center of the explosion can reach millions of degrees, far hotter than the surface of the sun, which is about 10,000 degrees Fahrenheit. In more familiar terms, the energy released in just a few microseconds can equal the amount of electricity used by a city of about 1 million people over 12 hours. That is why an atomic bomb is not just more powerful than a conventional bomb, it represents a completely different leap in how humans harness energy to create destructive force. But theoretical calculations are only part of the story. What happens when a weapon like this is actually used in war? In August 1945, the world saw the power of the atomic bomb used in war for the first time. On August 6, 1945, the United States dropped the first atomic bomb on Hiroshima. The bomb was called Little Boy. It used uranium-235 and a gun-type design. Its yield was about 15 kilotons of TNT.
This is Hiroshima, the day after the atom bomb exploded over Japan's seventh largest city and etched its message of doom to an empire. Heat traveling at the speed of light cast a shadow over Hiroshima and over the land of the rising sun. These films, taken by the Japs and confiscated after the armistice, tell a dramatic story of destruction and terror that followed in the wake of the first atom bomb loosed over a military target.
The bomb detonated in the air at an altitude of about 1,900 feet above the center of the city. Within seconds, about 4.4 square miles of Hiroshima had been devastated, and nearly 70% of the buildings in the urban area were destroyed. Extreme heat, shockwaves, and radiation collapsed homes, burned infrastructure, and caused widespread casualties. About 70,000 to 80,000 people were killed almost immediately after the explosion. By the end of 1945, the death toll had risen to around 140,000, as many more died from severe burns, injuries, and radiation exposure. 3 days later, on August 9, 1945, a second atomic bomb was dropped on Nagasaki. This weapon was called Fat Man.
We have used it in order to shorten the agony of war, in order to save the lives of thousands and thousands of young Americans.
Unlike Little Boy, Fat Man used plutonium-239 and a more complex implosion design. Its yield was about 20 kilotons of TNT, making it more powerful than the bomb used over Hiroshima. With just 2 bombs, 2 major Japanese cities were devastated. In Nagasaki, the city's hilly terrain made the zone of destruction narrower than in Hiroshima. Even so, about 36% of the city's built-up area was heavily damaged. The area hit hardest had an average radius of about 1 mile and covered nearly 2.9 square miles. About 40,000 people were killed almost immediately after the blast. By the end of 1945, the death toll had risen to around 70,000. Hiroshima and Nagasaki proved one thing very clearly. The atomic bomb was not simply a stronger weapon, it was a weapon capable of changing the scale of war in a single use. From that point on, the world entered a new era, one in which military power would no longer be measured only by soldiers, tanks, or warships, but also by the destructive potential of nuclear weapons. As of early 2025, 9 countries possessed nuclear weapons: the United States, Russia, the United Kingdom, France, China, India, Pakistan, North Korea, and Israel. Under the Treaty on the Non-Proliferation of Nuclear Weapons, however, only 5 are officially recognized as nuclear weapon states: the United States, Russia, the United Kingdom, France, and China. The other 4 still possess nuclear weapons, but they are not recognized under that framework. In numerical terms, the world had an estimated 12,241 nuclear warheads. Of those, about 9,614 remained in military stockpiles for potential use. Around 3,912 were deployed with operational forces, and roughly 2,100 were kept on high operational alert. Within that broader picture, the United States and North Korea remain one of the most closely watched nuclear standoffs. The relationship is built on deterrence, but each side views the nuclear issue in very different ways. As joint US-South Korea military exercises continue and North Korea keeps testing missiles, the tension has shown little sign of easing. This is also a subject Knox will examine in greater depth in future videos. In your view, which country holds the strongest position in today's nuclear balance? Share your thoughts in the comments and subscribe to Knox for more videos on military history, weapons, and the technologies shaping modern warfare.